Hello, welcome. Let's start going over game 6 of the second class handout. As always, we're going to start looking for dominant strategies. Player 1, if he's a lefty of a dominant strategy, up gives him 1 no matter what, down gives him 0 no matter what. Absolutely, this is an easy one, dominant. Player 1 is a righty. Up gives him 0 or 2, while down gives him 1. Definitely not. If player 1 is a righty, he does not know what he wants to do until he figures out what player 2 is going to do if up is played. All right, what about player 2? Told he's up here. Player 2 is told up is played. Would he want X or Y? Well, if he knew he was here, he'd want X because 1 beats 0. And if he knew he was here, he'd want Y because 4 beats 0. So again, player 2, if up is played, he can't figure out what he should do until he figures out where he is. What about down here? Player 2 is told down has been played. If he knew he was here, he would want Y because 3 beats 2. And if he knew he was here, he'd also want Y because, again, 3 beats 2. Another dominant strategy. All right. We've solved 2 of the 4 necessary pieces of our puzzle. Sometimes you solve 1 piece or 2 pieces that can help you with others. So let's go back. Let's look at the 2 things we haven't figured out yet and see if we now have enough information. Player 1, we now know, he knows if he goes down, he gets Y instead of X, but that really doesn't matter, does it? Because so what? If you're going to go down, knowing it's going to be Y and not X doesn't help you because you get 1 either way. So we really haven't figured out anything useful so far for what player 1 should do if he's a righty. And then what about player 2? If up is played, he knows that there's 2 possibilities, either just lefty goes up, which point he would want X, or both lefty and righty go up, in which point, well, if you work out the probabilities, he's going to want Y. So again, we don't really know. What about our tool? If there's a dominant strategy for player 1 going one way, we know the other way. So we know because lefty is going up, the only person who's going to go down might be righty. That doesn't help anymore because that would help us figure out what player 2 should do if down is played, but we already know what player 2 should do if down is played. So we're kind of stuck here. And I'm going to introduce a new technique. And this is just sort of saying, let's see what might happen. So the advantage for this kind of game is, there's 4 different decisions that need to be made, and each of them, there are 2 choices. So there's a limited number of possible outcomes. And it's possible to go through all of them and see which are no regret outcome. We've already decided 2 of the outcomes, and we don't know the other 2. So basically, there's 4 possible equilibria to check, right? This has to be, this has to be. We have to check whether this is up and this is Y, whether this is up, this is X, whether this is down and this is X, and whether this is down and this is Y. So we really only have 4 possible outcomes to check for no regret outcomes. And we can do that. 4 isn't too big. And I think a good way of checking is just to sort of see what happens, take a guess and see what happens. So when I write a circle around something, that means it's definitely going to happen. A circle with a D, of course, means it's definitely going to happen because it's a dominant strategy. But if I put a square around something, it means maybe. I'm not sure that's going to happen, but I want to consider the possibility. So let's ask ourselves, could there be an equilibrium with, definitely this and this Y, but also this up? I don't know if there is an equilibrium, but I'm just going to consider the possibility. What would have to be true if there's an equilibrium in which righty plays up? Well, there's only one more thing to figure out. What would player 2 do up here? Well, this would represent a pooling equilibrium, right? And player 2, if this were an equilibrium, would say, well, at 50% chance I'm here, 50% chance I'm here. That means if I play X, I get 1 half the time and 0 half the time. And if I play Y, I get 0 half the time and 4 half the time. I am definitely going with Y. So if there's an equilibrium where righty goes up, it has to be in that equilibrium that up leads to Y. I have absolutely not proved that this is an equilibrium because I haven't proved that there's an equilibrium with this up. all I know is if there is an equilibrium in which righty goes up, it has to also involve player 2 responding to up with y. So what I want to now do is check, is this a no regret equilibrium? I can check that because there's only 4 things to check. And remember, to check if something is a no regret equilibrium, I go through all the 4 places where people make decisions and I say, given what the other player has done, do you regret? Okay, let's see. Player 1 is a lefty. Does he regret going up given this y and this y? Remember, these are separate decisions. You can make a different decision up here from down here, but you have to make the same decision here and here. And you, of course, have to make the same decision here and here. So player 1, you're a lefty. Do you regret going up? Well, of course not, because you're playing a dominant strategy, but just to check, up leads to this 1, down leads to this 0. What if you're a righty? Do you regret going up given this y and this y? Well, up leads to 2, down leads to 1. Absolutely, you do not regret. You're happy with this. What about player 2 in this equilibrium? Does he regret? Well, he figures 50% chance here, 50% chance here, and you're better off given those odds with y than x. Now, this is a little complication because you could probably define regret if you wanted to in terms of what nature did. So clearly, if nature is going to end up going left, then you would have, preferred x to y. But I'm not defining regret in terms of nature. So this is important. When I say a no regret equilibrium, that is before resolving the probabilities that nature uses. So that is saying you don't regret given the probabilities nature uses and given the other person's strategy. So if you end up nature rolls the die in a way you don't like, but on average you made the right bet, you still don't regret. So just imagine someone says, hey, let's play a silly game, flip a coin. And if it's heads, I give you $5. If it's tails, I give you, flip a coin. If it's heads, I'll give you $1. If it's tails, you give me 50 cents. So again, someone offers a game. If a fair coin comes up heads, I give you $1. If it comes up tails, you give me 50 cents. Should you play? Well, yes. Now, if you flip the coin and it comes up against you, I'll still say you don't regret, because I'm just defining regret as before the probabilities are resolved. So player 2 does not regret. By the way, if you could watch me now, you'd see how silly I'm being. I'm making the hand gestures the way I'm making it in class, but obviously the camera isn't pointed to me, so that's really kind of silly. Okay, so you don't regret here, and player 2, of course, doesn't regret y for 2 reasons. First of all, it's a dominant strategy. You can't regret. And second, player 2 expects this decision to never matter in this equilibrium, so you can't regret. So this is indeed a no regrets equilibrium. Unfortunately, these kind of games can have 0 or more than 1 equilibria. So we've established there's at least 1 equilibria, and we've established in any equilibrium in which righty goes up has this y. But we haven't considered the possibility that there could also be an equilibrium in which righty plays down. So let me put a triangle around down, and this triangle means, hey, I'm going to consider this. Maybe there'll be an equilibrium in which down is played. Maybe not. So let's see. In an equilibrium in which righty plays down, we still know this has to be a dominant strategy, so this is played, and that still has to be played because it's a dominant strategy. But what does player 2 do in that equilibrium? Well, in that equilibrium, this is a separating equilibrium. And in a separating equilibrium, player 2 knows where she is. So if up is played, you know you're on the left, and you want x. Okay, what I've just shown is if there is an equilibrium in which righty plays down, it has to be that if up is played, player 2 goes with x. But I have not proved this is an equilibrium because I haven't proved there is an equilibrium in which righty goes down. So I got to go through all 4 of the decisions and see if there's any regret. Now, player 1 is a lefty. He doesn't regret his dominant strategy. Okay, fine. Player 1 is a righty. Well, if he goes down, he's getting 1. Had he gone up, he would have gotten 0. He doesn't regret. What about player 2? In this equilibrium, this triangle equilibrium, you know you're up here, so you don't regret x, and of course you don't regret your dominant strategy of y ever. So this is another equilibrium. So the first equilibrium, the square equilibrium, if nature goes left, then we go up and we end up here. So this is a square. And if nature goes right, we go here and we end up with y. We end up here. In contrast, in the triangle equilibrium, if nature goes left, we end up here. And if nature goes right, we end up here. So these are all the possible outcomes for this game. There's 2 equilibria. Now, which equilibrium will we get? I don't know. This is the equivalent of our simpler games where there can be multiple Nash equilibria. And I don't know which we're gonna reach. I would need some other criteria, and that's kind of beyond the scope of this class. So this game has 2 no-regret equilibria, the one marked by triangles and of course the circles, and the one marked by squares. And in both, if you know you're in that equilibria, you don't regret your actions. Again, I don't know which we're going to get, but both do count as equilibria. Thank you. Goodbye.